Swayam Prabha. Digital India. Educated India.
Okay, good morning. So in the last few lectures, we talked about vapor-liquid equilibrium of a binary mixture in the context of distillation. And now we'll be talking about some distillation operation that pretty much uses the VLE data. Okay, so the first thing I want to talk about is what is called this flash distillation. Another name to this is equilibrium distillation. Or sometimes also called as single stage distillation. Okay, so all these three names mean the same. So the idea here is we'll start with the liquid mixture, and then we partially vaporize this mixture, and then we'll have a separator where the vapor and the liquid will be separated from each other physically, and then you draw the distillate, you draw the residue, and that's it. And this constitutes one stage. If you remember our discussion about staging operation in absorption, this is what we did. We have two phases. They are come into contact for a particular time, and then they are physically separated. That constitutes one stage. So we can do the same thing for distillation, starting with the liquid mixture, partially evaporating, so that the vapor phase is created from the liquid phase itself. This is not a new phase, it's the same phase created from the liquid phase, and then because of the density difference you can separate these two. Okay, and then you can look at the composition of the distillate and the residual liquid. Okay, so that basically is what flash distillation or equilibrium distillation or single stage distillation. This can be done either in a batch wise, or we can also do it continuously. Let us start with a flow sheet that kind of describes how this operation goes on. So we have a feed. This feed is a liquid mixture of a binary system, binary species, and this is first sent to a heat exchanger, and we put some amount of heat, some some joules per hour or some joules per time. Okay, some amount of energy that we add to this, heat we add to this. Then we have what is called a throttling valve. So this is a valve, and this valve will try to change the temperature pressure of the mixture so as to partially vaporize the incoming mixture. And this stream is then sent to a large vessel. This is called the flash drum. This is supposed to be a cylindrical equipment. So you can see it's a flow sheet is very simple. We have got a feed, it is heated up by some sort of heat exchanger, and then it goes through a valve where the temperature pressure conditions are changed through some sort of a throttling process, isentropically, isothermally, or by other means. And then this mixture, so once this mixture comes out of the valve, you'll have a two-phase mixture. Okay, and this is basically sent to a very large flash drum. This is called a flash drum. So it's a cylindrical vessel, and you can see there are some baffles kept here, so that this mixture is actually sent tangentially to the drum, so it actually swirls away, and then because of the centrifugal force, and the separation is possible. The vapor will come out of this and the liquid will go down. Okay, very simple centrifugal force based separation of the two phases based on the density difference. And another important aspect is that this flash drum should be sufficiently big enough so that there is enough contact between the gas and vapor, so vapor and the liquid, so that the mass transfer can also happen. Ideally, what we want is, we want the vapor and the liquid to be in equilibrium by the time they are out of this flash drum. So that's why it's called equilibrium distillation. Okay. So there is a temperature and pressure corresponding to this particular flash drum operation. Corresponding to this temperature pressure, there will be an equilibrium composition for the vapor and liquid, and we allow enough contact time so that the vapor and liquid that is leaving this flash drum are at equilibrium. So the kind of question we may want to ask in this kind of operation is that we may say, well, there is a feed flowing at a particular flow rate, and we say it is a liquid mixture, and then we let's say we heat it, and then we adjust the pressure and temperature, and then we want to see what would be the composition of the vapor and liquid. Okay. So given certain flow rate of feed, given that we actually allow some generation of some amount of vapor, the remaining as a liquid, what would be the composition of the outgoing vapor? So that is the kind of design question we want to ask. You could ask the reverse question. You can say, I want my exit composition to be so and so, which are in equilibrium. How much fraction I should vaporize? Okay, this is a other way of posing the question. You can say, what is the fraction of vapor and liquid, and given that, what is the composition, or vice versa. Given the composition, what would be the vaporization rate, how much we have to vaporize. Okay, these are the design questions we want to ask. So let's start with the this question can be easily answered based on a mass balance, overall mass balance and species mass balance. Okay, so before we go further, let us also write the symbols that we are going to use. We will say that the feed is denoted by F in moles per time. Since I am saying it is a continuous operation, the feed is given as some F moles passing per unit time. That is the flow rate of the feed. And we will see that the composition in the feed is XF, mole fraction of A. Remember, A is the more volatile species in the mixture of binary mixture of A, B. So XF is the mole fraction of species A in the feed. Okay, and the feed can be liquid. So some amount of heat is sent here, and on the vapor side, we will say D moles per hour, moles per time, with a composition YD, and this again is for species A. So the molar flow rate of vapor is specified, and the composition of the vapor is also specified. The remaining 1 minus YD would be component B. Similarly, for the liquid, we will say W moles per time with the composition of XW. This is also corresponding to species A. So if you look at the overall process, the feed to the vapor to the liquid, all we are trying to do is, we are only just changing the proportion of liquid and vapor. Okay, there is only a physical change to the mixture, there is no chemical change. Okay, so that means that the total mass has to be a conserved quantity in this case. So we will write total mole balance as well as the species mole balance. So we say that this total molar flow rate F should be equal to D plus W. That means whatever goes in should come out. And then in terms of species balance, F times ZF, this is the number of moles of component A only, and that should be equal to D times YD plus W times XW. So the second equation basically says the total amount of species A is conserved quantity. Whatever that was there in the feed is now distributed between the vapor phase and the liquid phase, but still the total mole has to be conserved quantity, whereas this one is a overall total mass balance including both A and B. So now we have got two equations. In the second equation we have this F, and we can probably replace f or eliminate f using the first equation. So, we will say we will substitute for f is equal to d plus w. This comes from the first equation, and then write this remaining terms. So, after some elimination, you will be able to show that this yd minus zf over xw minus zf is given by minus w by d. Remember, w is the amount of liquid leaving the flash drum, d is the amount of vapor leaving the flash drum. Okay. So, this is a design parameter. We can actually control how much w, how much d should be there based on how we throttle the process, how we decrease the pressure or change the temperature. Xf is something that we know because this is a feed composition that is also under designer control, whereas this yd and xw are those which are corresponding to equilibrium values corresponding to VLE data. So, we can probably even cast this equation from a more graphical point of view in our the VLE data or XY data. So, for that what we will do is we will try to use let me start with let us consider a PXY diagram, okay, and then below I have XY diagram. So, what I am trying to do here is I am trying to cast this process, the flash distillation, into an equilibrium data to make sense of what this equation mean to us. Again, let me recall to you that this is a PXY diagram. The top one is the bubble curve and the bottom one is the dew point curve. Okay. At any given pressure, these are the two equilibrium compositions. So, if I have to denote the feed which is a liquid mixture, where would that point be in the PXY diagram? So, let us say XF is my feed composition, okay. Where can I denote a point that shows a single phase liquid phase mixture corresponding to ZF? Where would that point be in this diagram? Left side of what? The black curve that I show is a locus of all bubble points, right? So, where should I mark it? Should it be on the line? Yeah, draw a straight line. Okay, I draw a straight line. Then where would the feed be? Where do you locate the liquid phase? It should be somewhere above the bubble point, right? Somewhere above the bubble point curve is a liquid mixture, as a single phase liquid mixture at that particular corresponding pressure. Let us say this is a point before the mixture enters the valve. Okay, let us say at the valve we are trying to reduce the pressure. When I reduce the pressure, I come along this line and touch this bubble point. Okay, so bubble point is where the liquid will first form its first bubble. and the first bubble will have a composition corresponding to this point. But that's making only a one bubble, but you want to have sufficient amount of vapor. So you have to go deep further down. Let's say you come somewhere here. This is a two-phase mixture, okay, and these would be the corresponding equilibrium vapor and liquid composition. If you continue to decrease the pressure even beyond, you may even reach a point here where you would have completely vaporized all the liquid. The dew point line correspond to entire vapor and one dew drop having a composition corresponding to this point. And if you decrease the pressure further down, you enter into a completely a vapor phase. This has to be clear to you. In a TXY or PXY diagram, where to mark the single phase, vapor phase or liquid phase, and then how to draw the process when we heat it or when we change the pressure or we change the temperature. Okay. So this was amply discussed in the last 2-3 classes. So again, you have to pay attention to this. This is very, very important concept to conceptually understand these things. So what I'm trying to say here is that you have an option to choose a pressure in this range so that you will have a two-phase mixture. Above this window, you are either in the liquid phase or in the vapor phase. The distillation can happen only between these two range of pressures. Okay, and you can see this range is fixed by ZF. But if I change the ZF somewhere here, then you have a different range of pressures to operate. So that means the feed composition is also an important factor to consider about. Okay, when you have a choice to make the feed composition different, then you have to choose according to the operation condition that is available for you. So from the flash distillation point of view, what we are saying is we start the feed, okay, we heat it, and then we decrease the pressure along this line and reach a point somewhere here. Okay, so let's say this point is point F, and that point can be denoted here as this point, because here the average composition still is ZF, but then when this mixture enters the flash drum, you have the opportunity for the phases to separate, mass transfer to happen, so that they both can come into equilibrium. Okay, and that equilibrium composition is given by YD and XW. That can be somewhere here on the equilibrium line. Okay, so this is YD and this is XW, and you see there is a line that is connecting these 2 points, and that is the equation of this line that I am showing here. The slope of this line is given by minus W by D. So we can actually say this is the operating line of flash distillation. So this point lies on the 45-degree line. So this is ZF both ways. So what this tells me is that depending upon how much vapor and liquid I create by partial vaporization, the slope of the line will be dictated, and the point where this line touches the equilibrium line is the equilibrium composition. Okay, so now coming back to the question that we posed, we say we know the feed composition, and let's say we also know how much we are vaporizing, and we know the liquid and vapor composition. And then what I can do, I can start with ZF, draw a line with a slope equal to minus WD, and then extend the line till it touches the equilibrium line. And the point where it touches the equilibrium line is the equilibrium composition, and you read graphically the value of YD and XW. So that's the meaning of this equation. Now, since we are talking about the slope of the line that dictates what is the equilibrium composition is, what are the possible ranges of this slope? What are the ranges that we can have? I can have W by D equal to 0. What that means? Everything is vaporized. So that means this corresponds to which point? It corresponds to dew point. Okay, so this corresponds to dew point. Very good. And the other limit I have is W by D can be infinite, which this corresponds to which point? Bubble point. Yes. So here in the dew point, we are saying that we have just to have a saturated liquid and the first dew has formed. Okay, whereas in the bubble point we have pretty much the other way around. So in the dew point, what we are saying is everything is vaporized. Okay, so we can see that if I go back to this plot and I can draw the line corresponding to those conditions. So W by D is 0 corresponding to this line. Okay. And then this corresponds to W by D of infinity. So what it says is that if I have decided what my ZF is, the limit between the bubble point and dew point corresponding to those ZF are the choices for me. I can operate the flash drum or the flash distillation between these two limits. You can operate between the bubble point to the dew point, and you have access to reach any of these composition as equilibrium compositions, not beyond. Okay. So if you say that I start with the ZF, but I want to reach a composition somewhere here, and that's not possible, right? If you want to have something here, then you should actually operate at a different feed conditions. So in a way, the feed composition decides what range of equilibrium composition that are achievable by flash distillation. Remember, it is a single stage. You don't have much control. It's a single stage operation. Once the flash is happening, then the phases are separated and they are removed. Okay, there is no further purification possible. So you are asking in a single stage, what's the maximum composition I can achieve? The maximum Y is this, and the minimum X is this. Okay, and you have to have anything between. You can have a range of slopes depending upon how much fraction you are vaporizing. So we can make a following statement that the richest vapor corresponds to bubble point composition. So that is this point, and the leanest liquid corresponds to dew point. Which corresponds to this point, and the flash can happen anywhere between these two. Now, even though I said this is a flash distillation, you can also use the same process for what is called the partial condensation. Let's say you start with a vapor of a binary mixture, and then instead of heating you can cool it. You can decrease the temperature and then reach a two-phase mixture and then send it to the flash drum, let the two phases to equilibrate, and then you separate the vapor and liquid. This is a separation based on partial condensation. Partial condensation. This is basically opposite of flash distillation. So you have the same flow sheet that the feed goes in. You have a heat exchanger, but you don't add heat, you actually remove heat. Okay, remove heat, and then you send it to a flash drum. So in terms of the design equation, you have the exactly same equation, because the same operation, same flow sheet. It's only whether we add heat or remove heat. If I do an enthalpy balance to this problem, that will be slightly different. As far as the mass balance is concerned, it's the same thing. Okay. So, you can use the same set of equation I derived before for both flash distillation as well as for the partial condensation involving a single stage operation. So, now let us do a problem to actually kind of illustrate this concept. So, this is the exercise problem 9.5 in tray bulk. So, this is a kind of very straightforward question. So, what it says is that we have a liquid mixture and this contains 60 mole percent of acetone and 40 mole percent of water. So, we know the chemical makeup of the mixture A and B. So, acetone is A, water is B, and at 26.7 degrees Celsius is to be continuously flash vaporized. I have underlined flash vaporization because distillation can have other way of there are other ways of doing distillation. So, you have to keep an eye on what type of distillation it is. Okay. So, when we say something called flash vaporized, then we are talking about flash distillation or equilibrium distillation, and this is done at 1 atmospheric pressure. So, the flash drum is operating under 1 atmospheric pressure. So, here is to vaporize 30 mole percent of the feed. So, we know that the vapor that is coming out of the flash drum is 30% of the feed. Okay. So, D is specified. What will be the composition of the products and the temperature in the flash separator to be if equilibrium is established. So, in terms of the flash operator, they say flash separator pressure is to be maintained as 1 atmosphere. Okay. So, we have to find two things. One is what would be the composition of the products. Here the products are vapor and the liquid. What are the compositions? And what would be the temperature of this mixture if the two outgoing streams are at equilibrium. Okay, so, that is a question to answer. So, here you can see everything is mentioned in terms of percentage. Actual flow rate, feed flow rate is not mentioned. So, what we will do? We will take a basis, we will take 100 moles, we will take 1000 moles, so that it is easy to operate, okay, because it's everything is given in percentage. And we also need a VLE data for this problem, which is not mentioned directly in this problem, but this data is something is available for us from the data books. So, what we will do first is we will write the basis of 100 moles per hour of feed. Okay. So, this is a basis that we will do, and based on this feed the data says that the D is 30 moles per hour. The first mass balance that we used is F is equal to W plus D, and from here we know that W is nothing but 70 moles per hour. If I change my basis, these numbers will change, but we are not interested in the absolute number, we are only interested in the ratios of W and D, so that's fine. So the operating line for flash drum So now let's substitute what are the things we know. We do not know what is YD is, but we know what is ZF is, it's 0.6. Again here the component A is acetone, that's more volatile than water. XW also we don't know, and this is equal to minus 70 by 30. So this is something like minus 2.333, something like that. So this is the equation of line for the operating line. So now we need VLE data. So let me show you the VLE data. So here this is Y versus X, and this is obtained at P is equal to 1 atmosphere, because that's the operating pressure for the flash drum. So here we have to locate the XF. XF is 0.6 on the 45-degree line, and then we have to draw a line with a slope equal to minus 2.333. Okay, we know 1 point and I know the slope, and I can always draw this line. So I'm just sketching it here, but you can do it with a scale. Okay, so this is a line with a slope equal to minus 2.333. Okay, and then you see where it cuts, and from here you read the value of YD and then correspondingly XW. So from the XY data, you will see that YD comes out to be something like 0.837 and XW is something like 0.506. So here I have shown schematically, but you can do it in with a graph sheet and ruler. So the important point is to note ZF is there and the slope is known, and then you draw a line and cut the equilibrium line and then read the value of Y and X from this plot. The second question is about, if this is at equilibrium, what would be the corresponding temperature? Okay. So for this we need a TXY diagram for 1 atmosphere. I have that also. So we have a TXY diagram corresponding to 1 atmospheric pressure, and what we need to do here is the top curve is T versus Y and the bottom curve is T versus X, and this is temperature. Here got X and Y, right? So now I can actually locate the value of Y on the red curve. So YD is 0.837, so 0.837 is somewhere here, this is 0.9, so I can find 0.837 to be somewhere here, and then I go vertically and then I go to the red curve, because the red curve is TY diagram, and from here I can read the temperature and you can see something like 60 degrees Celsius. Or equivalently you can use TX curve, you can go to the black curve and then locate where XW is. So XW is 0.506, so 0.5 is somewhere here, 0.506 is somewhere here, and then from here also from the TX curve you can read the temperature, and you can see this is actually a coexisting temperature. Okay, you can either use TY curve or TX curve, both will give the same temperature because these 2 points are the equilibrium point corresponding to the tie line. So temperature is about 60 degrees Celsius. Now I can actually change this problem slightly differently. I can say that the drum was operating at 1 atmospheric pressure, and I will say the equilibrium temperature in that drum is, let's say, 75 degrees Celsius or something. If I mention the temperature from this TXY diagram, you can know what is the corresponding X and Y values. Okay, if I know the corresponding XY value, I can go back here and I can substitute X and Y, and then correspondingly I can get the ratios of the moles of residue to the liquid. Okay, so the same problem can be inverted and asked, given the ratios of the vapor and liquid, what would be the composition and temperature? or given the temperature and hence the composition, what would be the relative amounts of the vapor and liquid. Yeah, any doubts here? Okay, so let us do one more problem. In this case, we will do this partial condensation example. I believe this is also the example, yeah, exercise problem in tray ball. This is exercise 9.6. So the problem statement is this: a saturated vapor at 1 atmospheric pressure containing 50 mole percent acetone and 50 mole percent water is subjected to equilibrium condensation. So in the previous problem we said flash vaporized, so here we say equilibrium condensation, okay, to yield 50% 50 mole percent of the feed as liquid. Compute equilibrium compositions and equilibrium temperature. So in this problem, what we are saying is that if I have to draw this PXY diagram, in flash vaporization, flash distillation or flash vaporization, we come from liquid to the two-phase mixture. In the partial condensation, we do the opposite. We start with the vapor phase somewhere here, and then we condense it. That means we actually go somewhere here, and then corresponding to this point, there will be an equilibrium composition. Okay. This is corresponding to the operating condition for partial condensation. Okay, so again, we will take a basis of 100 moles per hour of feed. So the problem statement is that the liquid is 50%, so W is 50 moles, D is also 50 moles, so WD by D is just 1 and ZF is 0.5. So our operating line is YD minus ZF by XW minus ZF is equal to minus W by D, that is actually minus 1. So I can go back and then take the same diagram because I have the same VLE data. So here the feed is 0.5, so 0.5 is marked here, and then we have to draw a line with the slope of minus 1. So that would be something like this, and then you can correspondingly calculate Y and W. So the answer was YD is 0.8 and XW is 0.2. So that means this line has to be slightly, I think it should be somewhere here. And again you can go back to this XY diagram and find that corresponding temperature. So 0.8 is here, 0.2 is here, and this is the tie line. And you read the temperature somewhere here, I think it's about 62 or 63 degrees Celsius. So this is a tie line. This is YD and this is XW. and this is the equilibrium temperature. All right, okay. So let's go and just slightly summarize. So what we discussed here is a concept of flash distillation or equilibrium distillation or single stage distillation. So this involves taking a feed which can be a liquid or it can be a vapor. If it's a liquid, we vaporize it. If it's a if it's a liquid, we vaporize it. If it's a vapor, we condense it. Okay. The flow sheet is still the same. We have a flash drum in which the two created phases are allowed to phase separate. This design problem is not about designing the size of the flash drum. The role of the flash drum is to give enough contact time so that the two outgoing mixture will be at equilibrium. Suppose if this flash drum is designed such a way that there is no adequate contact time, what would be the consequence? Yeah, so mixing or mass transfer will not go to completion. Okay, that means the outgoing mixture need not be at equilibrium. From the pictorial point of view, you don't touch this point, you probably fall short somewhere here. So in the design of the flash drum, you have to have adequate residence time for the mixture to reach equilibrium composition. If it is under designed, the outgoing composition will not be in equilibrium, it will fall short somewhere here or maybe somewhere here. Okay. Now the question is, how do I know how much residence time to give? Then that is related to mass transfer rate and the flow rate of the vapor and liquid. If I know the flow rates and if I design the volume, from here I can find the residence time, and the residence time that is required will be determined by the rate of mass transfer between the two phases. So that's where the kinetics of mass transfer comes into picture. But as far as this particular calculation is concerned, we are not looking at design of flash drum dimensions, but rather we say there is an adequate, we are basically saying infinitely large sized flash drum. Okay, but in practice we need to have a sizing. Okay, and that sizing will have to take care of the residence time and equating that residence time to the time required for mass transfer based on the mass transfer rates. So here we looked at two ideas. One is this flash vaporization and flash condensation, and the operating line equation is very simple. It is based on the purely the mass balance, and then use this mass balance equation along with the equilibrium line such as xy or txy or pxy and get the corresponding equilibrium compositions. Okay, so since I said it's a single stage, all stage operations typically we assume equilibrium conditions. When we talked about absorption also, I said if absorption have to happen in a multi-stage sieve tray or bubble tray, each tray we assume to be under ideal condition, meaning the streams leaving the tray are at equilibrium. We can only do calculation about equilibrium stages, but in practice none of them are actually ideal stages. That's where the efficiency will have to come, and then we have to correct for it. Okay, so here what we did was equilibrium condensation or equilibrium flash calculations. Okay, so with that I'll stop here.